Okay, so today we'll cover just a few conceptual things, not a whole lot of calculation-based stuff, but conceptual topics, and based on that, and then so we'll do that. We'll have a quiz based on this the stuff I covered today next week, and we'll also have a bit of review today. We'll go through it. This week, your primary homework is to work through the practice final. Okay, there is a practice final posted online. Okay. Your assignment this week is to work through that. Also work on creating your note sheet, okay?
One page from that.
Yeah, you get 1 page, 8.5 by 11, okay, front and back. It can be typed or handwritten, okay? I'll supply a sheet of formulas online as well that you can use as kind of a starting point for your note sheet if you wish. You don't have to. There's no requirement that says this is what you have to use. Yeah. Oh yes. Okay, and what I recommend is do as much of the practice final as you can using your note sheet, okay? Okay, and then next week we'll go over all of the answers to the practice final, have some more review, and that'll be it. And then after that is the final exam. Question?
I haven't yet checked the example exam.
Okay.
So my question is, are we gonna get tested on finding the mean, the standard deviation, the things that we had done before?
No. So the final exam, you can expect, and I'll talk more about this next week. Final exam, you can expect about 80% to be stuff from chapters 7, 8, and 9, and then about 20% stuff from chapters 1 through 6. The stuff from before the midterm, that's chapters 1 through 6, will be conceptual or definition based in nature. Okay. Yes.
Do we have a quiz next week?
Yes, there's a quiz next week. Okay. And then I'll also produce a grade report for you that says if you want this if you want your final grade course grade to be this, you need to score this on the final, okay? So it'll say like if you want an A, you need to get 90% on the final. If you want a C, you need to get 65% on the final or something like that, okay?
If you wanna fail.
Yeah. Well, basically, if you don't get the lowest number there, then that's going to be failing, right? So, okay. Any questions? All right. Then we'll get into it. Okay. So there's one more topic in the class, and that is sampling methods, okay? Okay, so sampling methods cover how we select our sample. How we select our sample from the population. Because in statistics, the population is always, or is almost always, too big for us to observe directly, so we take a selected group and we study that. We study the sample. And of course, if we want our conclusions from the sample to be valid, our samples need to be representative of the population, okay? Okay, and so we have several sampling methods, and so the one that we've always talked about is simple random sampling, and I know I've talked about simple random sampling already, but pretty much almost all of our statistical inference methods assume that our sample was selected via SRS, okay? Okay, and with simple random sampling, requires that we have a sampling frame. Okay, and a sampling frame is ideally a list of every single person in the population. And so, you know, this is a difficult thing to do. If you don't have a perfect sampling frame, then your random samples will exhibit the same deficiencies. Okay, and then with SRSs, you just select individuals from the sampling frame, one at a time. You know, using some kind of random device, okay, or using a random method or random device. Yes?
So I noticed you wrote up there a person, but a better word for it would be individuals, right?
Yeah, every single item or thing, or, you know, if you might not necessarily be dealing with people or humans, you might be dealing with, you know, animals of some kind, or, you know, objects, bacterium.
Candies, M&Ms.
Exactly. So every single thing. Okay, but just in case they are people, it's, yeah, we have to designate those as people. Okay. And this means every individual has a equal chance of being selected, and every possible sample has an equal chance of being selected. Okay. And so that's simple random sampling, SRS. We have other sampling methods. One of them is systematic sampling. And there are, I should say there are many sampling methods and a lot of effort can go into sampling. And here, we're going to talk about this topic maybe for 10 minutes, 15 minutes, or I don't know, just a short amount of time, okay? And the truth is you can take an entire course devoted to the topic of sampling. You can dedicate your entire career working on sampling, trying to get real samples. And you have organizations like Pew Research and things like that, Gallup, that do these surveys that work really hard at trying to get representative samples. Because whenever you see in the news something about some research opinion poll, they say 62% of Americans feel about this, about that, that's usually coming from some kind of organization like that has devoted a lot of energy into getting good samples, okay? Which is it's a surprisingly difficult thing to do, okay? All right, so we have systematic sampling. This works best for systems where there is a queue or a line, okay? Okay, and the way systematic sampling would work is just select every nth person or individual from the line. So, for example, select every 12th person. Okay, and that would be systematic sampling. Again, if you don't have a queue or a line where people are kind of going through this system, then this method will not work as well, okay? But, sometimes you go through checkout at a, drugstore or something, and then they print out on your receipt, answer this survey, and you'll get a gift card or something. Now, some of those places print it out on every single receipt, okay? And others of them, they print it out on only every 10th receipt or something like that, okay? So things like that work for systematic sampling. We also have stratified sampling. Okay, stratified sampling, this actually makes the work of sampling a little bit more difficult. Makes a bit more work for sampling. We'll say it's most often used if the questions in your survey might be related to the demographics of the population, okay? When, survey responses are likely to be linked to demographic traits. Okay. So, I think Washington Post produced, had a story today about, they surveyed a bunch of people, does sexism still exist? Okay. And it turns out that if you ask men, most of the men said, no, I don't think sexism still exists. And if you asked women, a lot of the women said, yes, sexism definitely still exists, okay? So, the answers to questions like that are very likely to be related to the sex or gender of a person. Also may be related to, political leanings and things of that nature. And so, if you did truly random sampling, from truly random sampling by random chance, your sample could end up having a majority of women or a majority of men just from random sampling. And if your sample ended up being, majority male just by random chance, then that could affect the answers to these questions, okay? And so if you want your answer, the results of your survey to be, as representative as possible, you want to make sure that you are the demographics of your sample match the demographics of the population. Okay. So, in stratified sampling, the population, consists of different groups called strata. Okay, and then the samples are selected so that the sample, the strata, or the samples are selected so that the different groups in the sample have the same proportions as the population. Different strata within the sample Okay, so for example, let's say the population is 40% group A and 35% group B and 25% group C. Okay, then the sample will be selected so that it too is also 40% group A A, 35% B, and 25% C. Okay, because from random chance you might get 50% group A or something like that, and if the questions in your survey could be related to whatever group or strata someone belongs to, then that could throw off the results of your survey. So that would be stratified sampling. Okay, and then we have cluster sampling. Yes, question.
In Strata, how do you go about keeping it from being biased?
What do you mean from keeping it biased?
I mean, from being biased, if it has, it can usually be. I mean, it's very likely because of, how do you?
Well, well, the purpose of stratified sampling is to try to reduce the risk of bias by selecting too much of one group and not enough of another group. With stratified sampling, you're forcing your sample to have this much of this group, this much of this group, and this much of another group, so that at least according to that aspect, it mirrors what is in the population. Okay. Okay, and then lastly, we have cluster sampling. And cluster sampling is a method that is used to try to make our task of sampling easier, okay? Okay, and so with cluster sampling, you know, it would be very difficult. So generally, it's difficult to get a true sampling frame of the entire population. However, the population might naturally be divided into different subgroups, okay, called clusters. And then, and so with cluster sampling, you obtain a list of all the clusters, okay? Okay. And then randomly select some of those clusters. And then with these selected clusters, either perform a census, interview everyone in that cluster, or perform random sampling within the cluster. Okay, so for example, perhaps you wanted to survey everyone who attends church in Los Angeles, okay? Or not everyone, but you wish to survey people who attend church in LA, okay? It would be very difficult to get the sampling frame. It would be very difficult to get the list of every single person who attends church, okay? On the other hand, it would be a little bit easier to get a list of all the churches that exist in LA, okay? Okay, I mean, this task might be still a little bit difficult, but it's much easier to get a list of all the churches than a list of every single person who goes to church. Okay, and then so once you have this list, you might select, I don't know, 20 or 30 churches from this list at random, okay? Say, select some of the churches from this list at random. Okay, and then go to each of those selected churches and then perform simple random sampling or perform a census. Okay. Okay, and that would be cluster sampling. And this is, cluster sampling is, often employed for exit polling at, on election day and things like that. Rather than trying to randomly select, they randomly select different it's much easier to get a list of all the polling locations, and then they randomly select certain polling locations. And then probably, instead of simple random sampling, they would probably do systematic sampling. Every person who leaves the polling location, they might take every 10th person or every 5th person who leaves the polling location. Or, if it's a smaller location, they might get a census or something like that. But it's much easier to, get a list of all polling locations. That list is available to the government, and they can select things that way. Yes.
But then that leaves out the absentee voters.
So that will get factored in. So some places like Oregon only have vote by mail, or things like that, and so that gets factored in. So it like I said, sampling is much more complicated because in real life situations it is. But so that gets factored in, and so they say, okay, well, for this state and this state and this state, we can do cluster sampling. For Oregon, we got to do something else, stuff like that. So, and usually, they only do like if it's for the presidential election, they only go to the quote swing states, right? So, Oregon is pretty reliably blue, and so they probably won't do as much polling there. They'll just look at a few and they'll say, like, yep, it just as we expected, so we'll call it this way. And then, they go to what the swing states are, Florida, Georgia, Arizona, things like that, and Nevada. Anyway, okay. I get very excited for the statistical side of elections. It's very exciting for me, yes.
So, Professor, so for the systematic sampling, the key to know what that is if it's the 5th or the 2nd? Or...
Yeah, it's just pick some whole number, every 12th person or every 15th person, depending on how much traffic goes through or how long each thing goes, right? So, sometimes Google will experiment, or large websites will do experiments on changing the interface, okay? And this is called like A/B testing. And what they do is, every time they feed produce a web page for somebody, they might say like every 100th person is going to get this slightly modified version of the home page, and we want to see if the behavior of these people change a tiny bit, right? Like they might move the advertisement over here and they want to see like, oh, does the rate of people clicking the advertisement change? Okay, and they might do something like that, yeah. Yes?
So I noticed the second part you wrote down select some of the churches.
Mm-hmm.
When you select them, do you select them randomly?
Yes, yes, at random. Select some of the churches from the list. Yeah, at random. Yeah, right here.
Oh, sorry.
Yeah. So.
You were mentioning polling.
Mm-hmm.
Right now, in the textbook, it said like how the two t-tests, it said you don't do unpooled. So.
Oh, okay. That's pool. Pool like P-O-O-L.
Yeah.
Now I was talking about polling like,
So it's
this,
different.
yeah, P-O-L-L, which is asking for opinions and
Oh,
surveys.
I
Yeah,
see.
that kind of thing. Okay. Okay, and then so on the final, you'll have a few questions where I'll describe some scenario, and you've got to identify whether it's cluster sampling or systematic sampling or something like that.
And then, last
And-
thing, will we ever have to worry about like paired, like, in terms of the t-tests?
No, I don't. We have not covered that, and we won't cover that. Okay.
Just wondering.
Yeah. Okay. The question was about paired t-tests, and the answer is not covered. Okay. I mean, it might come up in your future education depending on what you end up studying. So, it's good to know that it exists. All right. Oops, that's not what I want. Okay. So now I'm going to cover a little bit of some more conceptual stuff related to hypothesis testing, okay? Okay, and so, just a quick review, it's, important that we understand the definition of a p-value, okay? And so the p-value is a probability, okay? It is the probability of observing our data, okay, or something more extreme, if we assume that the null hypothesis is true. Okay. And the decisions that we make based on the p-value, I think we've kind of covered this a lot, but I just want to make sure we have this down, is that, okay, if our p-value is large, okay, if our p-value is greater than alpha, then we say the p-value is large. Okay, and a large p-value means that the probability of observing your data is high, okay, even when the null hypothesis is true. Okay, so a large p-value means that even when the null hypothesis is true, we have a large probability of observing the data, or observing our data from random chance alone. Okay, and so this means that while it doesn't prove that the null hypothesis is true, our data does not cast any doubt on the null hypothesis, okay? So that's what we have. On the other hand, if the p-value is small, so if the p-value is less than alpha, then we say the p-value is small. Okay, and a small p-value means that if the null hypothesis were true, it is quite unlikely for us to get our data from random chance alone. It would be quite unlikely our data from random chance alone. Okay, the fact that we did see this data thus causes us to doubt the null hypothesis. Okay. Doubt or reject the null hypothesis. Okay, and so this is the idea behind using a p-value for making our decisions. Okay, there are problems or just inherent. There's an inherent possibility of making a mistake, okay? And this is actually not just something limited to hypothesis tests, but we'll talk about exactly this inherent mistake-making probabilities in the context of hypothesis tests. But just keep in mind, when we're doing statistical inference, we are trying to make a conclusion about the population based on limited data. Okay, because we don't want to observe the entire population, so we are looking at just a sample. And because we're looking at just a sample, we are inherently susceptible to making mistakes. Okay, and that's all of life. In that, anytime you make a decision without having all of the information, which is every situation ever, you could be making the wrong decision, okay? Because, you know, we don't know what's going to happen in the future, and so whatever it is, whatever major decision or even minor decision that you make, because we don't know exactly what will happen in the future, or we don't know all the details about whatever, the decision we make could be the wrong one, right? Like, should you buy this product now? Maybe, maybe not, okay? You're hoping that when you buy it now, it's not going to go on sale the next day, but it could, right? Well, and then you buy it from a reputable retailer that offers, you know, a price match for, you know, post-dated products and things like that. But whatever. Okay, so so we have errors that we cannot avoid. Because we are making decisions or making conclusions based on limited data, right? You know, or anytime you know, choose a love interest, whatever method that might be. You know, you only have limited information, right? If it's a little profile online, a picture with, 140 characters for a blurb or something. You've got to make a decision. Who knows, right? Whatever. Okay. So, we're making conclusions based on limited data, and ideally, we make the right decisions, right? Okay, so, in the ideal situation, we avoid mistakes, okay? Okay, and those ideal situations is, in reality, the null hypothesis is false, and our decision is to reject the null hypothesis. Okay, or in reality, the null hypothesis is true, and our decision is not to reject the null. Okay. But on the other hand, these are the errors. Okay, and when statistics was developing as a field, they said, oh, there are two types of errors we can make, so we're going to name them type 1 and type 2 error, okay? They didn't have creative names. Over time, we've kind of come up with slightly better names, but the type 1 error, we have type 1 error, okay? And this is often known as the false positive. Okay, so with the type 1 error, in reality, the null hypothesis is true, but our decision is to reject the null. Okay? We don't want to do that, but we might. That could happen. And type 2 error, we might call the false negative. In reality, the null hypothesis is false, but our decision is not to reject the null. And so those are the errors that we are susceptible to making. We have probabilities, and we give of making these mistakes, and we can assign values to them. Okay, and so the probability of a type 1 error this is equal to alpha. Okay, alpha being our significance level. Okay, so when we say alpha is 0.05, okay, that means we are accepting kind of a 5% risk of committing a type 1 error. And you might say, well, I don't want to make type 1 error, okay? Why don't I choose to use a small alpha, okay? So, why are we okay with 5% type 1 error? So the thing is, if we wish to reduce type 1 error, we can decrease alpha, okay? Right. But the side effect of that is that reducing your alpha will increase the risk of a type 2 error, okay? We can reduce alpha. So this will reduce type 1 error, but this will also increase the risk of type 2 error. Okay. And so the letter that we give type 2 error is beta, okay? So this is alpha and beta. So alpha is the first letter of the Greek alphabet. It looks kind of like an A, and that's the first letter of the Greek alphabet. Beta looks kind of like a B, and that is the second letter of the Greek alphabet. So type 1 is alpha, type 2, probability of type 2 is beta, okay? That's actually where we get the word alphabet from, putting alpha and beta together. And you get alphabet. But anyway, that's what we have here. Probability of type 2 error. So we get to choose alpha. Okay. We do not have direct control over beta. Okay. But we can influence beta by choosing to increase or decrease alpha. Okay. So okay, but it's not a direct, it's not a direct relationship there. All right, is this okay? Okay, so let me give you a few examples or scenarios where we have, type 1 or type 2 error and what that means, okay? And in some situations, type 1 error is worse than type 2 error, and in other situations, a type 2 error is worse than type 1 error. And depending on those situations, you may choose that you would rather have a large alpha or a small alpha, okay? Because we can accept that. So imagine a criminal trial, okay? Criminal trial. Some trials are decided by jury, some are decided by a judge. So let's just say you are in the seat, you're the judge or whatever, okay? So we got criminal trial now. We always say that the defendant is presumed to be what until the defendant is proven something else, right? So we always say the defendant is presumed to be innocent until proven guilty. So in this case, the null hypothesis is what we're going to assume to be true. The null hypothesis would be what? Yeah, so the null hypothesis is that the defendant is innocent. And the alternative is that the defendant is guilty. Okay, and we will say that only one of these possibilities is true. Okay, so for whatever charge is brought against the defendant, in reality, the defendant is either innocent or guilty, okay, of the charges the charge brought against him or her. Okay, and it's up to the prosecution to provide evidence to convince the judge or jury that the defendant is guilty. Okay, and if there's not enough evidence, then either the case will be dismissed or the jury will find the defendant to be not guilty. Right? So.
Or it's a hung jury.
Yeah, in that case, you know, a decision wasn't made, but the prosecution must present evidence. We'll say evidence to convince. We'll just say the judge that the alternative is true. Okay. If not enough evidence is provided, okay, then we do not reject the null hypothesis. Okay, so do not reject the null hypothesis means the jury or the judge would say not guilty, right? Do not rejecting the null hypothesis, this means not guilty. Notice that the jury never says we find the defendant innocent. The jury always says we find the defendant not guilty. In the same way, the trial, because it's up to the prosecution to present the evidence, it's not, we can never prove that the defendant is innocent, okay? Or they're not set up in such a way that the defendant has to prove innocence, but just that, you know, the burden falls onto the prosecution to convince you that the defendant is guilty. Otherwise, you conclude not guilty, okay? Found innocent.
So they're presumed innocent by the very fact that they're found not guilty.
Yeah, you presume innocence, but it's just that we haven't rejected the idea of innocence, okay? Okay, and so, you know, in ideal situations, the ideal case is that if the defendant is innocent, jury says not guilty, or we'll say judge says not guilty. And if the defendant is guilty, then judge or jury says guilty. Okay, so that's the ideal situation. All right, we have potential errors. Okay, and we don't want either of these, but what would a type 1 error be? Okay, let's. So type 1 error, this is the null hypothesis is true, but we reject the null, right? So that means the defendant is actually innocent. Okay? But the judge or jury says guilty. So that would be the type 1 error. And what is the type 2 error? I'm sorry?
That they're guilty in their plea.
Yeah, so this is the null hypothesis is false, but did not reject the null. So this is the defendant is guilty, but the judge or jury says not guilty. Okay. Now we don't want either type of mistake. We don't want type 1 error and we don't want type 2 error. Okay? But if we had to say one of these errors is worse than the other, so we want to try to avoid one of these errors more than we want to try to avoid the other error, which error would we say is worse?
Depends on your political persuasion.
Okay, well, all right. Type 1 error, okay. I feel that type 1 error is much worse than the type 2 error, right? I mean, type 2 error is bad. We don't want that, okay? Like, if someone's guilty, we don't want that person to go free. We feel justice has not been served.
How with type 2 is that you're going to have more victims eventually?
Well, so there's
So another innocent people who
But then in this
compared to this one perspective. But I understand you.
yeah, there is, okay, so there's always some debate here and maybe some philosophy, but the way our justice system is set up is it's set up such that the type 1 error is worse than the type 2 error, okay? So the way our justice system is set up is that the type 1 error is worse, okay? This error is worse. I mean, people might disagree and might say, we should set it up so that the type 2 error is worse, but and that's the way the justice system is set up in other countries, okay? And maybe it's because I've grown up in the United States that I feel this way, but I think it'd be worse to convict or if we're talking about capital punishment, to execute an innocent person than to let a guilty person go free. Maybe we feel differently, and it might depend on different situations. But as far as criminal trials, this is how it's set up. Maybe in civil cases where it's not an act of crime, but maybe an act of responsibility or things like that, or culpability, then it's set up a little bit differently. Okay, and so so in this situation where the type 1 error is worse, would we want a large alpha or a small alpha? If type 1 error is worse than type 2 error, okay, we would want a small alpha. Okay, so keep in mind that alpha is equal to the probability of a type 1 error. So by choosing a small alpha, the probability of committing a type 1 error is small. Okay, and they say this in court. Okay, they charge the jury before making a decision. What do they tell the jury about using a small alpha? They don't say, jury, use a small alpha, but they say what?
Use precaution.
you guys all have to agree to make 100%.
Okay, so you do. They say beyond a reasonable doubt. That's the phrase I was looking for. Okay, they say beyond a reasonable doubt. They don't want you to convict someone based on a hunch, okay, or based on just your gut feeling saying, I think this person is guilty, therefore I'm going to convict the person. They don't want you to, they don't want that. They want you to be sure beyond a reasonable doubt, okay? And this is, you know, so you don't convict someone to avoid, you know, wrongfully convicting someone. You know, based on, you know, quote. All right. Beyond a reasonable doubt, okay? But again, you know, they don't put the level to be 100% certain, okay? Because we can't be 100% certain about anything. So, you know, what would, you know, just imagine a scenario where, you know, a judge says, I never want to wrongfully convict someone, okay? And this is a reasonable feeling that a judge should have. A judge should feel like he or she doesn't want to ever wrongfully convict someone. But let's say someone says, you know, I never want to wrongfully convict someone. What is the only way someone can be sure that that the judge never wrongfully convicts someone?
Doesn't convict anyone.
Yeah, the only way you can be sure is if that judge never convicts anyone, okay? Because as soon as the judge convicts one person and says guilty, there is a possibility that that person who is guilty was actually innocent, okay? And, you know, unless you have all the information ever, which is not possible, okay? And so, you know, if, you know, a judge uses alpha equals 0 to avoid wrongful conviction, what ends up happening would be that no one ever would get convicted. Okay, and then the judge would not be doing the job of being a judge, okay? So this is, no one would ever be convicted, you know, high risk of type 2 error. And I'm sure the judge would be swiftly removed. Yes?
You're saying that we can never get 100% sure about if someone is actually is innocent or not. Though I think that in our society today, that you know, for example, if someone goes through a red light, what do you want to see? You want to see a video camera that shows that you went on a red light? That's like pretty much.
Oh, okay. All right. So.
Or if he's on drugs, you test him, you know.
All right. So maybe this is. So in certain scenarios, yeah, maybe you can get, you know, evidence, and there's a lot of questions going on, right? Like, so maybe we want to avoid type 1 error and we want to avoid type 2 error, but you can't have it both ways, right? You can't reduce your risk of type 1 error without also increasing the risk of type 2 error, okay? If you want to reduce type 2 error, you might, you'll probably have to decrease type 1 error. The only way you can possibly reduce both type 1 and type 2 error is by collecting more and more data, okay? And this is a possibility in the future, and there's a lot of questions about privacy, you know. We are kind of moving towards the point where we're collecting data on everything at all points in time. You know, we could have a situation where there's Big Brother watching us ever, and then, you know, maybe if we have all the access to all data ever, and know exactly everything, and every moment in time we can answer all of these questions of whether someone is guilty or not guilty, but then there's all sorts of other issues with that, okay, with privacy, right? I mean, as humans, I think we appreciate our privacy, and I mean that's a question that people, proponents of surveillance, always say, you know, what do people have to hide? But who knows, right? So these are just some questions, you know. Here we're just talking about hypothesis testing and the implications of large or small alphas, and just like whether you're going to reject the null hypothesis on whether your M&Ms are red or not. But a lot of these things do, you know, depending on how you apply these concepts, can have bigger implications. So so that's what we have. We got type 1, type 2 error. All right, what was beta again? This is the probability of a type 2 error. Okay. What would the quantity 1 minus beta be?
Alpha?
No? It's the probability of not committing a type 2 error, okay? Right, this would be, anytime you do 1 minus something, you get the complement, so probability of not committing a type 2 error. What is not committing a type 2 error? No? What?
Committing type 1 error?
No?
Or nothing at all?
Okay, here, let's look at this, all right. So a type 2 error, in a type 2 error, the null hypothesis is false, and what we do, okay, we choose not to reject the null hypothesis. Okay, so that's a mistake. So not committing a type 2 error, or type 2 error also can be the false positive, false negative, I'm sorry. False negative is the type 2 error. So not a type 2 error would be the true negative, in that the null hypothesis is false and we choose to reject the null hypothesis. So this is a good thing, okay? And so we give the name 1 minus beta. This is called power, and this is the probability of correctly rejecting the null when the null is false. All right, is this okay? I'm thinking of just continuing on, and then we'll just finish a little early today. Is that all right?
Yes.
Okay. Rather than taking a break. Okay. So everyone feels good about that. All right. Is this good? Any questions on this? So you'll have a quiz next week covering some of these topics, type 1 and type 2 error. You know, the situation I presented with the criminal trial, that was a situation where the type 1 error is worse than the type 2 error. In other cases, type 2 error could be worse than type 1 error. So for example, you could have like I guess I'll just write it really quickly, like a cancer screening, okay? And in that case, you know, generally the assumption would be you are healthy unless things come up in the tests that indicate that you are unhealthy or that you have cancer or something like that. And so a type 1 error, what would a type 1 error be? false positive. So you think someone is sick when in fact they are healthy, right? And then a type 2 error would be the false negative, where we think someone is healthy, but in fact they are sick or they have cancer, okay? And in that situation, the type 2 error would be worse, okay? Or, if it's, I don't know, something like Zika virus or something like that, right? It would be worse if we think someone doesn't have the virus or doesn't have the disease when in fact they are carrying it, because then it could be transferred to other people or something like that.
We could have a weird baby.
And yeah, those are, that is the primary symptom of that. So, okay, or negative effects. Okay, so I'm gonna just do that. So, situation. Okay, so we'll say, so the null hypothesis would be patient is healthy. The alternative would be patient has cancer. Type 1 error, the false positive. Patient is healthy, but we believe he has cancer. Okay, but the test says type 2. Now both of these are errors, and we want to avoid both of them. But I think the false negative is worse. But the doctor believes the patient is healthy.
Well, one can be corrected and one can't.
Well, so both can be corrected with more information, right?
Maybe not for the patient though.
Yeah. Right. You can't go back in time. That's true. And so this is so a lot of times, and it's not like cancer diagnostics are just like this easy thing. You just step in a thing and it goes, this is what you have. There's steps. So if you're a guy, you're supposed to do a testicular self-exam every month. If you're a woman, you're supposed to do a breast self-exam every month. And basically it says if anything seems a little bit weird, go see a doctor, right? That's a test with a very high alpha. The slight thing that's weird, go see a doctor. And basically it's not saying if you have the slightest thing that's weird, you have cancer. It just says go see a doctor. The doctor can do something a little bit more thorough to evaluate. But the idea is these self-exams are supposed to basically have a low risk of type 2 error, okay, higher risk of type 1 error, because type 1 error, not that big of a deal. You have to go see the doctor. Maybe you pay your copay or things like that. The negative side of a false positive for something like that is not that bad, whereas missing early detection could be a bad thing, okay? And that's why sites like WebMD, it's anything you look up, it's maybe cancer, right? And that's because, if you're doing any kind of self-diagnostics, they just want to make sure that, well, maybe you should go check out the doctor, right? I guess the only negative side of having such a high alpha, where everything is being flagged as a false positive, is that we joke about WebMD now and think oh well, WebMD says it could be cancer, but I don't believe we don't believe anything that WebMD says now, right? So cancer or pregnancy. Yeah. So those are all the symptoms. Okay.
Well, the other side effect is the high wait time at the doctor's office, because everybody's going in.
Yeah,
So
that's
they think they have cancer.
yeah. If if you have too high of an alpha, then there's definitely problems with that. You don't want to go too extreme on either side, but so a balance needs to be struck. But in this case, type 2 error is worse, so we would choose a larger alpha. Okay. And as type 1 error gets worse and worse, like you want to reduce your type 1 error. So like if you do a self-exam and you find something a little bit strange and you go to the doctor, they're not going to immediately say, okay, well, let's start chemotherapy right now. They're going to, because that's a very serious thing to go through. And so they do more tests because they want to make sure they want to make sure things are they have the correct diagnosis before starting something quite traumatic. So all right, okay, we'll start our review. Okay, so as far as statistical inference goes, we've covered 7 different topics. Yeah, question.
So we're done learning new material?
Yeah, that's it for new material, okay? So this will be our review. So as far as statistical inference goes, we've covered kind of 7 different topics. We've got confidence intervals. We had confidence intervals for P, 1 sample. We have, I'm going to just write confidence interval for mu, 1 sample. And we have confidence intervals for mu1 and mu2. Or it's really mu1 minus mu2. And that's 2 samples. Okay, and then we also have hypothesis tests. We have hypothesis test for P, 1 sample. Hypothesis test for P1 and P2. That's 2 samples. We have the confidence interval for mu with 1 sample. And we have the confidence interval for mu1 and mu2 with 2 samples. Okay. And as you work through the kind of the practice final and the final exam, it's going to be critical that you can identify whether you're dealing with confidence interval. I meant hypothesis. All of these should be, sorry. It's very important that you can identify whether you've got confidence intervals or hypothesis tests, okay, and whether you're dealing with means or proportions, and whether you have 1 sample or 2 samples, okay. So you must identify which situation you are dealing with. You know what? I'll pass around an attendance sheet here. sure to print your name in the attendance sheet today. Okay. So you have to identify which situation we're in. Okay. All right. And so let's see. If the data is categorical, you will be dealing with proportions. Proportions, which also mean the Z table. Okay. If the data is categorical, you can tell if it's categorical because the data will be presented either as a proportion or as counts of successes. Okay, proportion, or I guess percentages. Okay, and on the other hand, if the data is numeric, you'll be dealing with means. Okay, and here, you know, the problem will probably say something about average or mean will appear in the problem. In problems with means, the standard deviation will need to be given. Okay. So if no standard deviation is provided, then it can't be a problem with means. Okay. Try to identify how many different sample sizes you can find, how many different ends there are. Okay, so you know you will need two ends if you're going to have problems with two samples. All right. Okay, and then whether you're dealing with a confidence interval or a hypothesis test, okay? So confidence interval problems will always mention a confidence level, okay? Confidence level. So it'll say like 95% confidence interval, or you know 90% confidence interval. It's got to be somewhere in there. If it doesn't say anything about confidence level, you can't do a confidence interval problem. Okay, I mean that's probably going to be the clearest indicator of whether it's a confidence interval problem or not. Okay, as far as hypothesis tests go, I mean it sounds silly, but you know, if you see the words hypotheses somewhere in there, then you know it's a hypothesis test. If you see, you know, perform a test or a p-value, okay? So, you know, you don't use p-values for confidence intervals. So either, you know, hypothesis or, you know, p-value or test, things like that. These are all indicators that you're dealing with a hypothesis test. Okay. So, you know, look at the problem, decide whether you're dealing with confidence intervals or hypothesis tests, whether you're dealing with proportions or means, and whether you have 1 or 2 samples. Okay, and that's the most important thing because that's going to shape everything else. We good there? Okay. All right. So let's talk about all of our confidence interval stuff. So we got confidence interval for P, and then I've got a confidence interval for mu, and then we have confidence interval for mu1 minus mu2. So we never covered confidence interval for P1 minus P2, and I think that's fine. That's I don't think we're missing out too much. No. Yeah. I don't think anyone. I don't feel bad skipping that topic. Okay, so I would feel bad if we skipped out certain topics. This one, that topic, it just doesn't happen very often. You generally hypothesis test for P1 and P2. That happens. Confidence interval P1 minus P2. Rarely. Okay. So this is P hat plus or minus Z star times the standard error. Okay? Standard error is the square root of P hat times 1 minus P hat over n. Yes, question?
Are you going to provide us the Z star?
So, the Z star, there are 4 of them, right? Yeah, so same 4, okay? So you just, have these written on your note paper, okay? I'm not gonna give you the formula sheet, all right? If I have posted a formula sheet online, okay? If you want to use that as the sheet you're going to use on the final, that's fine. That's up to you, all right? If you want to make your own, because some people like to make their own thing, that's your prerogative. This is America. You're free to do what you want, right?
Oh, wait, I thought it was
So 80%. Okay, and then we got 90%, 1.645. All right, and then that's that. Okay, and the question will be like, does the interval provide evidence that P is something else? Okay, does the interval provide evidence that P is different from some number here, right? Okay, and how do we answer? We just see if this number, the box, is in the interval or not, right? Okay, for mu, x bar plus or minus t star times the standard error. Standard error is s over the square root of n. T star comes from the t table. And degrees of freedom is equal to n minus 1. Huh? Oh, this is mu minus mu2. Mu1 minus mu2, and we're going to cover that one. Okay, and then pretty much this thing works the same way as this, right? We got x bar 1 minus x bar 2 plus or minus t star times the standard error. Standard error is s1 squared over s2, or s1 squared over n1, s2 squared over n2. T star also comes from the table. Degrees of freedom equals n minus 1. Use the smaller of n1 and n2.
And round down, right?
Always round down, yep. Always round down with the t-table. Round down if you cannot find the exact degrees of freedom. Okay, and then for the confidence interval for mu1 minus mu2, we'll say the question is, does the interval provide evidence that mu1 and mu2 are different? And how do we answer this question? Okay. If 0 is in the interval, what does that mean? No evidence of a difference. Okay. Is the sign-in sheet going around? Who still needs the sign-in sheet? Okay, that whole side. All right. Okay, and if 0 is not in the interval, then you have evidence of a difference. Can we ever prove that mu1 is equal to mu2?
No, we don't have 100% evidence.
No. Yeah, we would need to see the entire population to see if mu1 and mu2 are equal. Okay? All right. Good?
Home sweet home?
What about the phraseology for number dose?
It's kind of like this. It's the same as this, okay? Except instead of p, put in mu. Okay. Does the interval provide evidence that mu is different from box? You know, check to see if box is in the interval or not. If it is, then no. If it's not, then you do have evidence. Okay. Okay. All right, and then I'll just go over the hypothesis test stuff quickly, and then we'll be done. All right. All right, so we got hypothesis test for P, and then we have the hypothesis test for P1 and P2, okay? So the null hypothesis is that P is equal to some number P0. The alternative is that P is not equal to P0, or P is greater than P0, or P is less than P0, okay? You know, and so for example, if P is equal to, 0.64 or something like that, okay? Figure out your standard error. P0 times 1 minus P0 over n, okay? You should always check your conditions, but you can assume, at least for all the problems in the final and things like that, the conditions will be met. There will be one section where you check the conditions, but for all of the other problems where you're doing calculations, the conditions are met. So you don't have to spend time doing that step, okay? And then your test statistic, which is always observed minus expected, is going to be P hat minus P0 divided by the standard error. This is your z-score, and then you look up z in the z-table to get your p-value. Over here we've got P1 equal to P2. Thank you. Everyone signed this? We're good? Okay. Okay. Also written as so first you get it for over here, you got to figure out your overall p hat. So that's going to be x1 plus x2 over n1 plus n2. Get your standard error. And then your z is so that's what we have for hypothesis testing for proportions. I guess I can list off, and in both of these cases, you know, if the alternative has greater than sign, p-value is equal to the area to the right of z. If the alternative has a less than sign, then the p-value is the area to the left of z. And if the alternative has a not equal sign, then p-value is 2 times the tail area. And that applies to both the 1 sample and 2 sample situations. Good? All right, and then we've got hypothesis tests for mu and hypothesis tests for mu1 and mu2. And then that'll be it. So those are your hypotheses. Your test statistic, T, is x bar minus mu0 over the standard error. And then you look up T in the T table. Over here, you got mu1 equal to mu2 as your null hypothesis, or mu1 doesn't equal mu2, or mu1 is greater than mu2, or mu1 is less than mu2. Also can be written as mu1 minus mu2 equals 0, mu1 minus mu2 doesn't equal 0, or is greater than 0, or is less than 0. Standard error in this case okay. You get your standard error, you get your test statistic T, look up T in the T table. Okay, So basically what you're going to do is you're going to use, over here, degrees of freedom is n minus 1. Use the smaller n. And over here, degrees of freedom is n minus 1. And then you find, which columns t is between. Okay. And then if the alternative has greater than sign, then p-value is the right tail area. If the alternative has a less than sign, p-value is the left tail area. Meaning, t is negative. And if the alternative has a not equal to, then your p-value is 2 times the tail area. Okay. And then in all of these, you make your conclusion, right? P-value greater than alpha, do not reject the null. P-value less than alpha, reject the null. And that's all of the hypothesis tests. When you don't reject, you don't have evidence. When you do reject, you do have evidence. Okay, that's that. We'll see you guys next week. Work on the practice final. We'll go over all of the answers to that next week. Okay, have a good night.